Okay, some problems from section 9.5 and numbers 1 and 2. We're supposed to use the integral test to determine the convergence or divergence of the series. So let's take a look at this. Number 1, this was a series, and the corresponding function would be 1 over the cube root of x rather than 1 over the cube root of n. And we want to check this for x greater than whatever this is, and this is 1. And f is continuous, positive, and decreasing for x greater than 1. And we can use this abbreviation a little bit later, CPD, continuous, positive, and decreasing. So the equivalent of this, we know that if that's the case, if this is the case, then this series will behave like this integral. In other words, if this converges, this converges. If this diverges, this diverges. So let's take let's take a look at this and evaluate this improper integral. So we have to change this to the limit as b approaches infinity of 1 to b of 1 over x to the 1/3. Same thing as that. Dx, and that's going to be the limit. I can put this up on the top to x to the minus 1/3, and then I'll add 1. So that'll make that positive 2/3 divided by 2/3 when I take the antiderivative. Let me evaluate that from 1 to b. And that'll be the limit of, and I can invert multiply 3/2 b to the 2/3 minus 3/2 1 to the 2/3. I don't need to worry about this because this is the main thing. This is going to go to infinity. Okay, infinity squared to the cube root of infinity. It's going to be infinity squared will be infinity. So this whole thing is going to go to infinity. So therefore, this integral diverges. Okay, it doesn't have a value. So therefore, my corresponding series diverges. Okay, again, this diverges, but it's a converges. Again, this diverges because it doesn't have a value. So therefore, since the improper integral diverges, the series diverges. All right? Okay. Let's take a look at number 2. Again, the same directions. So again, we'll look at the series. And we have n to the negative 3/2, or I'll write my function f of x as 1 over x to the positive 3/2, just to check and see if for x greater than 1 it is continuous, positive, and decreasing, and yes it is, so it is CPD. So I know that this series will behave as this improper integral does, so that's the integral from 1 to infinity of x, and put it back to the top, minus 3/2. So I'm going to take the limit as b approaches infinity of 1 to b of this x to the negative 3/2. And then what I will do when I take the antiderivative, I'll add 1. So that's going to make it negative 1/2, and I'll divide by negative 1/2. And then we'll invert multiply, so we have negative, and then 2 on the top, and then I can put this on the bottom. And I'm going to evaluate that from 1 to b. So I'll take the limit of that. That's going to be negative 2 over b minus, this is from your f of b minus f of a, and this is from your expression over here, your antiderivative, negative 2 over 1. So this is going to be negative 2 over b plus, and then negative has a negative is positive, pardon me, positive, yeah, that's what I meant. And then 2 over the square root of 1 is just 2. Now if I take the limit as b approaches infinity, this is just going to be what? Well, that's going to be really, really big. So it's going to be 2 over infinity, which would be 0. So it goes to 0. This stays at 2. So I have 0 plus 2, which is 2. Therefore, the value of this improper integral is 2. It converges to a particular value. Therefore, the corresponding series converges by the integral test. Okay. Okay, and the next one, this was just kind of number 3 was just a exercise in taking a look at the harmonic series and evaluating partial sums. So it's just a little arithmetic here. You could have done this a little bit easier by grouping terms and keep adding, but this is the summation from n equals 1 to infinity of 1 over n. That's the harmonic series. It's a special case of the p series. And we just want to find the first 6 terms, so s of 1 would just be 1 over 1, s of 2 would be 1 plus 1/2, s of 3 would be 1 plus 1/2 plus 1/3, which is common denominator 6. We put everything over 6 and get 11/6. S of 4 would be 1 plus 1/2 plus 1/3 plus 1/4. And the LCD for all these is 12, so you put everything over 12, and it's not that difficult. S sub 5, so we add a 5, so 5 times 12 is 60, so that's going to be our LCD. It just happens to work out that way. So it's not so hard to put everything over 60, and we get 137 over 60 if you add those up. And then I said, well, S of 6 is just 1, 2, 3, 4, 5, the first 5 terms plus 6, so I already knew what the first 5 terms was, so I saved myself a little bit of room here. And effort, and I just made this 137 over 60 plus, and I put this as a common number 60, so that'd be 10 over 60, that's 1/6. That ended up being 147 over 60, and both these numbers were divisible by 3. 3 goes into 12, 4 with 4 left over, so that's 27, goes into 9 times, and 3 goes into 60, 20, so that was your sum. Okay. And then number 5, I think we can get number 5 in here. Use the limit comparison test to determine the convergence or divergence of the series. So we look at our series over here, and as n approaches infinity, it behaves a lot like, well, the negative 1 and the positive 1 become kind of insignificant as we get such big n's getting out to infinity. So it behaves a lot like this, and this is kind of like the n behavior we've talked about earlier. It behaves like 3n over n squared. But then I can cancel the n, so this behaves like 3 over n. And if we take out the 3, it behaves really basically like 1 over n. And that's our divergent harmonic series. Okay, so we're going to compare it to 1 over n, but that diverges by the p-series test. Okay, that's our special case of the p-series test. So we'll compare it and see what happens. So we'll take 3n minus 1 over n squared plus 1 over n. And if we take a look at this, we invert and multiply, so we get 3n squared minus n all over n squared plus 1. Now, there's a couple ways you could do this. You could use L'Hopital's rule twice, I think. The first time you'd get 6n, I guess, minus 1 over 2n. And then if you took it again, you would get 6 over 2, which would be 3. You could do it like that, or you could just remember we can use our rational function method where we're finding horizontal asymptotes. That if the highest degree is the same, we could look at the ratio of the coefficients, and that's 3 over 1 because these are both 2. That's the highest degree. So that's 3 over 1, so that's 3. Now 3 is between 0 and infinity, obviously, so that tells us that they behave the same way. All right? So since this diverges, and they behave the same way, this series will diverge. So we can say that the summation from n equals 1 to infinity of 3n minus 1 over n squared plus 1 diverges because 1 over h diverges. That's by the LCT, the limit comparison test. And I like to use these little abbreviations to kind of notate what test I'm using, so I can keep track of the different tests, because there's a lot of them, and they can be confusing. Hope those help.